in industry are trying to predict the patient if he has some disease or not. I'm going to have my prediction. The only way to check it is to ask the doctor, is that prediction correct or not? That was our pipeline. The other thing that I want to recap is how this feature matrix looks like. Right? So what is a feature matrix? We have a data point x1, which is x11, x12, x1d, and x2, which is x21, x22, x2d, up to xn, xn1, xn2, up to xnd. That is the feature matrix. Every row here corresponds to a data point or data object, like a document, web page, patient, email.
So REC means it's on.
What?
Right? REC means it's on. How do I make sure it's on? Or how do I make sure it starts?
It's recording right now.
It's right now.
Yeah, I have there's a red dot in front of it that when it's recording.
Okay,
I see
yeah.
that. Thank you, Ketchen. Ketchen won't stay in class, but he'll set up sometimes the camera. And if you want to see him today, come at 6 p.m. in Writers Building. Every column in here is called a feature. So this is feature 1. That's feature 2, feature 3. So when I say the feature third of the data is the age of the patient, that means this is every data point, that's the age. The features have to be consistent. That's typical through all the data science, not just machine learning. When we say feature 1 is, person ID or name or date of birth, that has to be for everyone. Feature 1 has to be the date of birth. You can't have some data points with feature 1 being the salary, and for other ones is the date of birth, and so on and so forth. Nothing will work that way. So we expect some consistency. Now, there'll be some missing values in here. For some people, we would not know their date of birth. In that case, we may have a question mark or a missing value, but it's still part of that feature. We're not going to say this data point doesn't have a date of birth, therefore has D-1 features. It doesn't work that way. Still have D features, but we mark the ones that we don't have values for whatever reasons. That happens all the time. We don't have all the time all the values. And then we need typically 2 feature matrices, because we have the training and the testing, or the production one, supervised learning. But sometimes we might think of a big feature matrix, and we say, okay, some part of it is the train part. This is the train set. That's a bunch of data points. And this other part is the test set. So sometimes, and there is a additional wrinkle here. It's useful to think of it as a feature matrix, global, with all the data points, the training and testing. In particular, for the normalization issues, which we're going to get to in maybe today, maybe next time. So when we talk about data here, one big item is normalization. So what I typically do with minor things like this, some of you are not going to like this approach. I let students figure it out first or struggle, and then we iron it out at office hours. So like there's some blah, blah, blah about normalization in the textbook and in my notes and in the homework, and people get sometimes, okay, I heard about it, sometimes I don't know what it is, how does this work, It's useful for you guys to take a shot at it before me saying it exactly how it works, just to get a sense of why that's necessary. And then we're going to figure it out in class or at office hours. It's not hard at all. So normalization has to do with somebody gives me a feature matrix somehow. They don't even think about it as a feature matrix. Somebody may extract word counts from documents, for example, right? Like an index. But they didn't plan to use machine learning on it. They just extracted in this document how many times the word Virgil appears. That's 3 times. How many times the word Northeastern appears? That's 1 time. How many times the word, Boston appears, so on and so forth. That can happen. for some storage or for some indexing purposes. And then I get that data, trying to do machine learning on it. Normalization, it's necessary when features are totally out of scale. So one is the salary of a person, for example. That could be in the hundreds of thousands as orders of magnitude. The other one is the age. That could be, into like 0 to 100 integers. And the other one is a binary feature, 0 or 1. Now, while that's all good, the scale of it doesn't match at all, right? 0, 1 is a different scale than 0 to 100, different scale than 0 to 300,000, which is people's salaries. Some algorithms don't need normalization. Like this one here, decision trees, typically doesn't need a normalization. Whether we do normalization or not, we should not see big differences in behavior and performance. But some algorithms that we're going to study next week, like linear regression, definitely need normalization, because the magnitude of the features, the mean, for example, is a big one. Okay? So we have this. Now, evaluation of course, we're going to have some measures. So one measure that I want to point out right now is accuracy. Which is number of data points with labels correctly predicted. I say proportion. I don't think that needs a definition. Everybody understands this. If I say accuracy is 65%, I mean on 65 of the test points, I've got the right answer. That's what it means. But I want to point out some things about accuracy. There are binary problems. Let's do that here. Data here. What is a binary label? A binary label means, it's a yes/no type of label, like sick versus not sick, spam versus not spam, right? A tiger versus not a tiger. That's kind of a binary problem. What should my accuracy be if I have a binary problem? I'm trying to predict for patients if they're sick or not, right? If I use a random, I don't do a prediction, I just toss a coin in the air and get the result from that closest coin toss, What should be my accuracy if I do that? Yes? 50%. Easy to tell. Basic statistics, right? Well, so I definitely expect my algorithm to do better than 50%. Right? 50% is random. Worse than 50%, it's an adversarial, it becomes an adversarial issue. If I see my algorithm doing less than 50%, somebody's playing games with me, right? Probably. But I could have a multi-class problem. Multi-class, where for example, if I predict a color, that might be red or green or blue or black or yellow. Right? I know it's one color that I have to predict, but the options are 5 options, not 2 options. Right? In binary case, it's 2 options. In the multi-class case, there's more than 2 options. If I have this exact problem, red, green, blue, black, and yellow, what's my random if I toss coins and throw dice and all that? What accuracy should I expect? 20%? Right. Even if it's unbalanced data, so suppose I have that problem, but the vast majority of my data is red. So I have 5 labels, but most of my, I'm having clothes, and most of my clothes that I'm selling are red. If I throw coins, uniform coins in the air random, and I predict randomly by the coin, will I still have 20% accuracy even though my data is 90% red? So I'm asking this as a more like, I want to check how much statistics you guys know. So I have my data. I think everybody can agree that if I have randomly 20% red, 20% blue, 20% green, so on and so forth, a random prediction, uniformly random, will get me 20%. What if my data is very unbalanced and I still do a random prediction? I flip a coin in the air or a die that has 5 faces, and it's uniform, I pick one at random, that's my prediction. Would I still get 20%? This is something I expect you guys to know, or to go home and figure it out very quickly. Okay? It's still 20%, even if data is very skewed. If you pick something at random, you still have a 20% chance of picking the right color. Even though red is the right color 95% of the time, when I pick a random color, which is 5 possibilities, the chance of picking the correct one, red or blue or whatever it was, is still 20%. And that averages out to 20% over if I do it for all data. So this is the kind of basic statistics that you have to know. Now, suppose I know my data is vast majority red. I'm at this problem here. I don't want to do a dumb algorithm like predictions, but I'm not smart enough to do machine learning. What should I do? What should I predict? Always predict red. And if red is 90% the color in my data, I'll be right 90% of the time. So I'm going to take now this argument to extreme. I'm Google. Right? Somebody asked a question. What's the weather going to be? When is the hurricane going to hit? Who's the next terrorist? Whatever. Now, I'm classifying documents. You see that if you take an information retrieval class into relevant and non-relevant, that's very basic. Usually there's grades to it, but let's say, just say some documents, links are good and some others are bad, right? Google has an index of 10 billion documents, right? I'm trying to classify out of those 10 billion, which documents or web pages are relevant or good for that user who asked that question. How many documents for some query, any query, particular query, would I expect to be good? It may seem like a lot to you because you see a list of, Google used to say this in the result. Hey, I found 300,000 documents relevant for you in 1.5 seconds. Remember when they say that? They don't say anything, right? So you say like, wow, 300,000, that's a lot, right? The 300,000 might be a lot. Google doesn't even know if all of those documents are good. They just estimate they are good, and the most relevant of them are the ones you see at the top of the list. But it's still not that much out of their 10 billion, right? So my point here is that if you think of that as a binary problem, yes, no, right? From Google's perspective, I'm trying to classify for a given query, is the document good or not good for the user? As a binary problem, it's very, very skewed, right? For any particular query, the percentage of documents in the Google index that's relevant, even though it may seem a lot to you, that's very, very small. It's about 0.00001%. So in terms of accuracy, I'm getting back to the random prediction. If I want a high accuracy, I work for Google, and I say, Google, I'm going to have a very high accuracy. What can I do to classify those documents? Yes, right? And that's going to be right 99.9999% of the time, which is, of course, useless for Google's users, right? So you can see how data skewness affects evaluation measures and how we think about what's correct and incorrect. Accuracy, which is very basic, what percentage of data I've got correct, may be quite misleading, right? I've got 99.999 correct, but that's completely useless. So in that case, in this particular example with Google Web Pages, we need a different measure than accuracy. Accuracy is not good for that. We need a ranking measure. We're going to get to it at some point. Right. So I have binary labels. I have multi-class, and I may have some other ones later on. So first thing about accuracy is that you should ask yourself, when is this a meaningful measure? Like you're going to see the spam-based data set for homework 1, that's spam emails, and there's like 4,000 emails and like 50 features already extracted. So you don't see the raw data, the raw text, you get already 50 features extracted in the spam data set. This accuracy makes sense as a measure of how well an algorithm does. It makes sense in that case, but because I don't have this skewness. Okay? So I have this thing with measures here. Now, in research or academia, what we're doing here, we're not putting things in production right? So it's not like in this course, we're gonna run an algorithm and we're gonna put it in a production, as in train a model, go to a hospital with it, take the patients and predict their disease. We're gonna have the test labels. When we do supervised learning, we're gonna have those labels so we can evaluate our algorithms, right? So somebody asks, is it possible that when I do this train, let's say the train is 80% and the test is 20%. That's a very typical split in both academia and industry. Is it possible to get very lucky on very unlucky? Like when we do this split in training versus testing data, say I have images or patients or emails. Is it possible that I've got a hard set to learn from with a lot of mistakes and outliers and an easy train set, test set, so that accuracy I observe on the test set is higher than it should be? Or the other way, I've got an easy training set, but there's some misvalues and data shifts maybe, and the test set has very hard data points to predict. So my accuracy that I observe is 60%, but should be higher. Definitely possible. It's harder when you have a lot of data, right? There's a law of large numbers that says if you have millions and millions of data points, issues like that, being lucky or unlucky, are harder to observe. Yet machine learning has been concerned with this for quite a while. So there is a standard procedure for how to avoid these things. That standard procedure says, how about we cut the data set not in 80% and 20%, cut it in 5. So we call it this fold 1, fold 2, fold 3, fold 4, and fold 5. So now this is the same matrix. I just pick 20% to be fold 1, 20% of the rows, 20% of the data points, 20%, so this is 20%, 20%, 20%, all of them. So how can I avoid being lucky or unlucky? I do my training and testing, I do my pipeline here 5 times. First time, I'm going to choose, I want 80% training, 20% testing. So first time, I'm going to choose folds 1, 2, 3, 4 for training, and the last fold for testing. Right? So I run my algorithms 5 runs. The first one is, this is folds 1, 2, 3, 4, and this is fold 5. Then this is run 1. Run 1. Then I get run 2. I get folds 1, 3. Let's say pick another 1, 2, 3, 5, and that's fold 4, right? And then I get run 3, folds 1, 2, 4, and 5. That's fold 3, so on and so forth. You see how this is going, right? So that way, it's much harder to get lucky or unlucky. In fact, it's impossible if you do this problem, right? No matter how data distribution is. Some of these must contain the hard data points, and there'll be occasionally in training, otherwise in testing. But you gotta be very careful. These runs have to be completely independent. So you have to run the whole pipeline to call it a run. Train, call the test on these models, have predictions, and run the evaluation. So in here, I have an evaluation. So on this run, I get accuracy 62%. On this run, I get accuracy 67%. On this run, I get accuracy 60% alone, right? And then I'm going to average these accuracy numbers at the very end. So I have to run the complete pipeline for each fold that's testing. And this whole process here is called cross-validation. Now, this is independent of what algorithm I use. Our focus on this course will be on particular some algorithms, like decision tree is the first one, but this pipeline can be repeated with any algorithm. And it's not necessary if the data come partitioned. If some data creator already decided that's the test set, that's the training set, then we follow that partition. We don't need to repartition it into folds.
What will be the final model in this case?
So that's for testing a particular algorithm to get an accuracy. What he's pointing out is that if I do this, I actually get 5 models, right? So I still have to use one of them, right? There are ways to average the training process to get one model, but that's not our concern right now. In practice, so why is he asking that question? That question is relevant only if I go to production, right? If I want to know how good a decision tree is, I run it 5 times, I get 5 models. Each model is tested on the appropriate fault. I get accuracy values, I report my accuracy. I'm going to say my decision tree algorithm implemented by me produces a 63% accuracy. Now, the question is, which model should I actually use? It's relevant if I go to production. If I go to a hospital and I'm trying to really predict the next patient, whether they have the disease or not, I need one model, right? But in most cases, when I go to real production environments, I don't worry about cross-fault validation, right? I'm going to use the previous patients, they have labels for training, and the new patients that I don't have labels for testing, right? I mean, this is only relevant if I have the labels so I can play with those faults. If I wouldn't have the labels for my production environment for some data, I couldn't use this as a training set anyway. I don't know if that's clear enough. I think this is an exercise to test the algorithm, right? To say, okay, I want to have accuracy, to report an accuracy of it that's not lucky or unlucky. But then when I go to production environment, typically I have whatever training data is given to me and whatever production data or testing data that I have to predict on. I have no option to decide which data point goes to training versus testing in production environments. Okay, so that's kind of where we are here. When I'm going to connect my projection, I'm going to talk a little bit about the homework and logistics. So let's move to decision trees. That's our first algorithm here. Before we go to decision trees, I want to talk about something called data rules. Or heuristics. That's not machine learning. Those are rules designed by humans, typically with trial and error expertise. You know? For example, if fever is more than 100 degrees, it implies flu. A patient has flu. If email contains the word free or the word porn, that is spam. If age is smaller than 22 and high school has high school diploma, is eligible for college application. I have a funny one here. If romantic genre is yes, and comedy yes, and Orlando Bloom. Yes, let's talk about movies, right? Then success. Sorry, that's what's written. Now, you see where I'm going with this. People have figured out those rules, and some of these rules were critical if you look at the history of civilization. Imagine military. Julius Caesar was a great general, or Augustus, or Napoleon, or you know, but they didn't have the ability to study even battlefields the way we have it now, right? So how did Julius Caesar or Napoleon figure out how to win a battle? Trial and error, of course. But he came up with rules like this. If I have so much cavalry and the other guy has so much, infantry, and this is the terrain, and what I know and this and that, I'm probably gonna win. If something else happens, I'm probably gonna lose. I have other rules here. NASDAQ. Gain status and Apple announces new iPad, then buy Apple stock. And here's another one. Blood pressure. By logarithm of age. I think that's made up. I don't think it's real. So on and so forth. Banks use rules like this for lending money. They are the kind of the first digging into mathematics of risks. People who lended money. The banks really started in the Renaissance era, but even before that, when you go to somebody to lend you money, they had to develop some rules like this. What do I know about this person? How likely is to pay my money back? What's his business? What's going to do my money? How well do I know him? Is he young? Is he old? Does he have kids? So on and so forth. So rules like this have been developed all the time in construction, military, finance, everywhere. That's kind of what we want to do with the decision tree. We want to come up with rules like this, but not by human trial and error. Instead of trying it out and losing the battle, we like the decision tree to look at the data and figure out what's there. And actually, they're going to be very, very similar to what's here. So how can we do this from data? We start looking at data in a certain way. Say, here's my data. That's all data. To get a rule like that, or multiple rules like this, we're gonna produce a data split. So we're gonna have here, this is called a split. Let's say, maybe three. Usually it's in two binary splits, but we can have it three. And what the rule we wanna have here that here we have some data that passes on this branch. Data branch 1. This is we have data branch 2. We have the data. So these are disjoint sets. In terms of the as set data points, we can say B1 union B2 union B3 here is all data. And any BI intersect with any BJ is empty set. So every data point went exactly on one branch. There are variations of these complicated trees that allow other things, but for now, a split means I look at my data, and by that split, that has to do with my feature matrix, of course, I decided that data point, that patient or email or image or web page goes to that branch. Now, this is a partial data, right? It's not all the data anymore. It's only the data points that satisfy that condition. There'll be a condition here. I can repeat the process. I can look at this data here and say, well, I'm going to split this into a different split. So this is a split here, but it's a different split than here. So in here, I'm going to have some partial data let's call it B31, and this is partial data B32. Same property. B31 with B32 union as sets is B3, and their intersection is M. So this split conceptually is no different than that split. It's a different criteria, but that's the same thing. Out of the data points in here, some of them went that way, some of them went that way. This eventually is going to create rules like that, because each condition gonna act like age or fever or blood pressure or financial thing. It's gonna say if this, then that, right? If I split this one again, a data point, you can imagine a data point traveling in here. If the first condition applies, it goes here. The second condition applies, it goes here. And then the third condition applies, it goes here. This would be the data set B312. This would be the data set B311, and this would be B313, right? By the time a data point travels all the way here, it must satisfy the condition to go on that branch, and on this branch, and on this branch. So I have a sort of, if it's romantic, and comedy, and Orlando Bloom, right? This might be the romantic. Yes. This might be the comedy. Yes. And this branch here might be Orlando Bloom. So what movies end up in this group here? The ones that are romantic and comedies and have Orlando Bloom in them. That's how I get the data root. It's a path from the root of this tree to some final leaf. Of course, I can break it down even further by other criteria, right? So this decision tree encodes rules like that. Every path from the root down to the leaf, it's effectively a rule. We could actually take rules that are given to us by humans, like doctors. Doctors have those rules all the time. In fact, they're quite against machine learning algorithms. We have a hard time convincing doctors, hey, we can learn from data quite accurately. Sometimes we can discover things that doctors didn't think about, because maybe that's not so intuitive about why something happens with the drug or with the patient and so on. But we can take the rules as encoded by humans from previous knowledge, from trial and error, and represent them to the tree. Now, I have to figure out a few things. I show you guys in principle how this data structure looks like. What is this tree? It figures out criteria, splits by that criteria. So we have to answer a few things about this, right? What is the purpose? Like, why am I doing those splits? When to stop splitting? How to make predictions? How to design, how to find splits. This is in principle what it's going to look like, but I have to know those four things, maybe more than four things. When I decided, okay, don't split anymore this branch. What's the overall purpose of doing this? How do I, once I have this tree, presumably based on training data, because all the algorithms create a model. This is a model. This is one of these ML models that was on the board here. All algorithms are based on training data. So wherever you see supervised learning, decision tree, or any other algorithm, the way you build the model is based on a training set. And then I have to make predictions. Once I have this, I have to take a new patient or a new email or a new image and somehow come up with a prediction for that image. So let's see. How do we, what's the purpose? So what's the general purpose of a decision tree? What would I like to happen? It's very related to when to stop. presumably I'm going to stop when I'm close to achieving my purpose, right? And if I'm not close to achieving my purpose, I'm going to keep going. So those two are very related questions. Why would I do a split? I have my data. What's the point of splitting it? Yes.
Are you trying to classify data into like different categories in the end, like ultimately functional buckets to look at? Even binaries.
Right. So I think what you're saying, these three branches here have to be related to the labels that I'm trying to predict somehow, right? I mean, if I wouldn't have labels, if I'm in an unsupervised world where I have data like images but no labels, I could try to split them in many ways, right? And they could be all valid. Your way to rearrange images might be different than my way to rearrange images, different than her way to rearrange images, because we all have different criteria. There's those user studies that show some people thought of, here's a bunch of pictures with humans. I classify them by who's young versus who's old in those pictures. Somebody else classified them by how the people dress up. Somebody else classifies them by who wears glasses, and so on and so forth. These are all valid groups of data. But when we have labels, remember we're in a supervised learning realm right now, so we have labels. This is far more specific. We want to organize those groups in such a way that they play out somehow better with the labels. We need a little bit of mathematics to define this. How do we say these three groups are more correlated with the labels than the one before the split? So we need a mechanism to say, if I have spam emails, right? I have a bunch of emails here. I could say two classes, class yes, it's 60%, and class no is 40%. Binary problem. After I split the data, what should I expect if I really split it with those labels in mind? Those yes means spam, no means no spam if I have a binary problem, right? What should happen after I split? Yes?
At least in one of the sub-branch you get the complete yes or no. Like
That would
all-
be ideal. I'm not going to try to get ideal from the start. What should I hope for?
So we should get close to yes and close to many no's in each section.
What you mean is this proportion 60-40 for each one of those buckets should be more?
More like 90, 10,
Right.
80.
Well, I would like to get more skewed. I would like to say this is yes 90% and no 10%. This may be no 80% and yes 20%. And this is yes maybe 75% and no 25%. A decision tree calls that progress.
When you're splitting them, if you got it to yes 50%, no 50%, that'd be an improvement or worse.
I think that'll be worse from 60-40. But I think it depends of what you're gonna do next. But in general, with machine learning and many other algorithms, especially if you took most of you took a CS 5800 algorithms class, there is a notion of global objective versus a greedy local objective. So you can see here that somebody might do the greedy best split that you can find in this one shot, but overall when you look at the whole tree, maybe that was not the best first step. That happens all the time if you study greedy algorithms. The greedy immediate step may not be the best step to do. So that may have to play with this. But in general, we use a greedy approach that says you want to improve from 60-40. So we call all these three buckets improvements. We have to measure it as a whole. Maybe I have two buckets that are improved and one that is not improved, but overall still I get an improvement. For now, I mean, we're gonna get to technicalities, but can everybody see why this is better? So initially, if I take a random guess, I'll be 50-50 like I said, but if I take a more educated guess, I would predict yes all the time, right? Because yes is in the majority class, just say yes all the time, you're gonna be right 60%, it's better than random. However, if I have these buckets, if I know in which bucket my data point is, I can make a much more accurate guess. In here, if I predict yes, I'll be right 90%. In here, I predict no, I'll be right 80%. And if here, I predict yes, I'll be right 75%. Now it does make sense maybe to split this one again, right? 75, 25, maybe I get a yes here, 95%, no, 5%, and in here I get maybe a no, 82%, and a yes, 80%. I made up those numbers. So this kind of answers the first two questions. What purpose do I have with those splits? I want to organize the data to be more correlated to the labels that I care about. That's critical with the labels because many organizations make sense for different labels. So this has to be related to the labels that I'm actually trying to predict. And when do I stop? I stop presumably when I see something that's accurate enough, right? If I have 95 to 5%, I may decide that's skewed enough towards one end, either the yes or no, so I don't have to stop it, to keep splitting. Hands up, who's with me so far? As in, you follow me and you feel good about it. When I say this hands up, who's with me, I mean, that's a good time to ask a question if you are confused about it. Okay, so, right, let's assume I have this tree now. Somehow I build it up. How do I make a prediction? I have all this tree, it's organized, so I have these labels, right? This is yes, so I'm splitting this again, I get the yes, 99% here, no, 1%, again, yes equal 98%, no, 2%, no here, 5%, yes. So suppose I have these numbers for every single terminal leaf. The terminal leaf is the ones that are not splitting anymore. Somebody gives me a new spam, a new email, or a new patient. How do I make a prediction?
We find out the bucket that it most closely resembles and go
So
to.
I take my patient here, right? I have to know how to do the splits. That's essential. The splits, whatever information I have that patient, I have to know which way the patient goes. That's equivalent to applying, I have to know about the movie that's romantic, I have to know that's a comedy, and if it has about Orlando Bloom anyway. So I take my email and I say, which branch doesn't go? This branch. From here, where does it go? Here. Or from here, maybe it goes here, so far, when I get somewhere. And when I get to the final node, what do I do? Right, but what decision? So if I end up in this node here,
Yes.
I'm going to say yes, because yes is the majority class, right? Then I can also get the confidence depending where I am. But we're not worried about confidences right now. I think it's clear that once I pass a movie or an email or a patient to this tree down, where I end up is where I can say, well, where you ended up, the majority of the training points in that leaf were 98% yes. So I'm going to predict with high confidence that's a yes. Easy, right? I mean, that's easy. Decision trees are the most easy machine learning algorithm because they don't require much math. They're very easy to understand what they do and very visualizable. You can actually see this with emails. You can pass them to your tree and see why it happens that way. They don't have mathematical models. They don't make any assumption about the data. Like regression, if you've heard of, you make a linear assumption about the data. Naive Bayes makes an independence assumption about the data. So on. Decision trees are universal. They do not make any assumption about the data. So why not use them all the time then? Right? Neural networks is what everybody uses today, even if you don't know what that is. We all know Facebook and Apple and Microsoft, and everybody uses neural networks like Tesla cars. If the decision trees are so easy and so good, why use algorithms that make a lot of assumptions, some of them false about the data?
Maybe there are more like thousands of features and it becomes a big tree.
It could become big, right? That's one issue. So if I keep splitting until I'm happy meaning a good skewed either one way or the other. I don't want to stop at 75, 25. I could go way down.
Like the subset becomes so small that it's unreliable.
Right. So that has to do with the deep depth, right? The more down I go, remember that every data group here, every leaf is disjoint. All the data points that are here, they pass to this path, but they are totally disjoint to the ones here and the ones here and the ones here. So if I build a big tree, my data is going to be fractioned into small parts. So I could have something here, this 85%, that may be only 3 data points or 5 data points. And this one might be, 300,000 data points. So I end up with some nodes that are very, very small regions of my data. I could end up with branches that are very long. What else? It's a problem here.
It might not be true for the test data.
It might not be true, or you mean appropriate, or?
Yeah.
Right, so I don't know exactly what you mean, but there is an issue here, what's called overfitting. A decision tree can overfit, related to what has been said. If I make these buckets very small, like I go down into 3, I end up with 1 or 2 data points bucket. And while that is correct for that data point, this particular data point is perfectly described from the path here. It only applies to that exact patient. That whole bucket here will not apply to any other patient, right? Meaning, if my path in here describes perfectly one movie, it has to do with the authors, with the genres, with the actors, with the musicians, everything that's in that movie. Well, it's only one movie that follows all these branches, right? That is producing that year, that has the following actors, that's a romantic comedy, it's only that movie. So this model would not be useful to predict other movies with it because no other movie will fit exactly in that branch. That's a very typical property of decision trees. It happens all the time.
When adding a feature, new feature to the data set.
What do I do? That's a problem for all algorithms, not just decision trees. So I could mess up a regression or naive Bayes that way. I mean, it may be true that some are more fixable than others, but it's not necessarily easy to add the feature once you train a support vector machine. You still have to retrain it. And we're not particularly concerned in the first machine learning course, this one, with that problem. Ideas like this may be a project. There's an option in this course to do a project and to waive a homework if you want, with something original like this, like something that's not part of the course. If my data shifts or changes, my features become irrelevant, I have new features, how can I retrain my model to take advantage of that? We don't do this in the class, but if you want to do that, you can do it as a project. So, what else is bad about decision trees? So I can tell you the good things. Decision trees can learn from any data, no matter how hard, no matter how big, with no model's assumption. And eventually their accuracy at those leaf nodes will be very, very high. Because nothing's stopping me to keep splitting and splitting until I get consistency. We call this consistency. Consistency means when the vast majority of labels on some leaf, it's of one kind. So we say that everybody, effectively every data point in this branch is a yes, because it's 99%. So there's nothing to stop a decision tree to keep splitting and splitting and splitting until it has 100% accuracy on every single leaf. What's the only theoretical exception when that's not possible? How can I get a data set for which no matter how hard I split, I won't have 100% accuracy? Yes?
You have 2 points that have all the same training features, but then
Differently. So if I have 2 patients that are completely identical, one is sick, one is not sick, both patients will always be in the same bucket no matter how hard I split, but there will be 2 different labels there, right? But of course, this data makes it hard for any algorithm to learn properly, right? If I start having data points that look identical, they're not distinguishable, but they're confusing because one is yes, one is no. Except for that issue, decision trees can be driven with 100% accuracy. Of course, they become very impractical. They become overfitting trees that are not useful for predictions. So a more practical question is, when to stop. It's a good idea to stop early. In fact, most algorithms today that use decision tree, which are quite a lot of machine learning in production is based on decision trees. They don't like deep decision trees. They would rather have shorter decision trees, one-step decision tree, and then compensate some other way to it. Maybe add another decision tree, maybe do something else, rather than driving a very deep decision tree, which becomes not useful. Good. So we're almost done.
Yeah.
How to find a split? So what is a split? What are those criteria, right, that we talk about? Split, the branch 1, branch 2, branch 3. I'm going to put the feature matrix again on the board here. That's my feature matrix. And I'm going to also add the vector of labels. So this is a y1, y2, yn. These are the labels. Or targets or annotations. Right? Usually we don't include those in the feature matrix conceptually, but sometimes the data comes with one column that's designated label, so you have to pay attention. In the spam data set, I think the first column has the labels. But when you think about conceptually, we want to treat this as a feature matrix X, and this is a vector of labels. Now, this makes sense in binary 1, 0, 1, 0, or as quantities like salary. The salary of people, that may be the value of a salary. But it's not immediately clear how to make categories. If I predict red, blue, green, what should be the Y's? And if they're red, blue, green, how do I make a computer understand that as a category? There's some engineering there. But suppose we have this. What are the splits? In theory, we can design a split in any way we want. So we can take any rule, for example, something like this, and make a split out of that. Right? We can say, try if this feature plus this feature minus that feature, whatever, then something, and if that doesn't happen, then something else. Keep in mind that this has to be complementary. So whatever doesn't go to the first two branches have to go to the third one. Every data point has to go somewhere. It's not possible to design a split that says some data points will go here, some data points will go here, and some data points will go anywhere. We'll stop. All the data has to advance. Okay, this is. So, in theory, I can have an enormous number of splits I can choose from. I could say, for example, split, to the complicated one. Branch 1 is x1 value plus x2 multiply with x3 plus x4. This is for a particular data point I. So I have a data point I, and I look at the features 1 and 2, and I multiply feature 3 and 4. If this is bigger than 0.5, then that's branch 1. And branch 2, since I only have two branches, branch 2 must automatically be the complement of branch 1, is xi1 plus xi2, xi3 plus xi4, smaller or equal than 0.5. Those are complements. This quantity is either bigger or smaller. So I could try something like this. The reality is that we cannot afford to do this, even with supercomputers. There will be too many splits to try. How do I put my hands on rules like this in advance? So the reasonable splits that we can try, that's limiting the power of decision tree very drastically, is to say a split has to be only one feature. So you pick a feature for a split, and it has to be based on the threshold. So a split is pick a feature and pick a threshold. Or, so let's do here, splits are numerical. That's be binary. If X feature I call it F, f is bigger than some threshold, then that's branch 1. And branch 2 is when that feature is below the threshold. Yeah, those are complementary. The other splits are categorical. If my feature is categorical in nature, so for example, the color of my car, right? I could have branch 1, xf is red, branch 2, the feature is green, and branch 3, the feature is blue, and maybe branch 4, the feature is black, and maybe I have a branch 5, the feature is other color. So this split will say, take that particular feature f, it's a categorical feature, and by the color of it, you go that way or that way or that way or that way. For numerical features, something like age or salary or time to process data, you probably only have by 2 branches. It's bigger than thresholds, more than thresholds, but we need to find this threshold. So the advantage here is that we don't have a threshold. We just go by the categories. Here it's only 2 branches, but typically we need to find the threshold. So now we have to go down in the how to find splits down in the weeds here. We're gonna look for features and thresholds. Brute force. Unfortunately, for decision trees, the only way we know how to do this is to try all features and thresholds. We don't have an intelligent way of getting at feature thresholds. Now, there's some shortcuts with caching, something that I've tried before. I can keep around, so I can, use that as a previous computation. But nobody knows an intelligent way to train a split without literally looking at all features and all thresholds. And the other way is, how do we formulate the criteria for good split? Right? I mean, we already said that we would like this data to be more skewed. That's what we said. Whatever the split we choose, we would like, if this was 60-40, this would be 90-10 and 80-20, something more skewed at 60-40. But we have to write now that mathematically. So we need math. How do we say we want the distribution or the partition here to be more skewed than it was before the split? We're gonna have to find some mathematical way to say that, right? Because it's not like you're gonna look at it with human eyes, right? You're gonna have to plug in some formula on a computer, and then the computer figure out what's the best fit. So now, given those 2 things, we're getting very close to train a decision. Because this is brute force, it's up to you who write the program to figure out, how do I look at all features and thresholds, apply this mathematical criteria to all of them, and keep track of the best one and use that one, right? I mean, it's a simple max problem. Try all possibilities, see which one does the best, and use that one. And when I move to the next split, I do the same. Try all possibilities, features and thresholds, compute the criteria that I have, the mathematical criteria for how good that was, and then use the best one that I can. So the only thing remaining here is to figure out, how do we say this skewedness mathematically? We need a little bit of a math here. One of these other things, when I said statistically, I want to know how fast you guys can figure that out with a uniform, toss a coin, see what percentage I get. Here's another one. I have a distribution. Classes. P1 is 10%, P2 is 20%, 25%, 25%, and the last one is P5, 20%. It has to sum to 1, right? How do I measure skewness of the thing? How do I want a mathematical formula that says, indicates how skewed it is, right? This is binary distributions, but on a die that has 6 faces, I have a 6 slots distribution, right? This is a 5 distribution, sums to 1, that's 50%, that's the other 50%. I want a mathematical formula that measures how close to uniform is one extreme, skewness will be the other extreme. So this is a distribution that's not uniform. Here's a uniform version of it. All PIs will be 20%, right? If I have 5 PIs, this is uniform. And very skewed. P1 will be 99%, and then P2 will be the same as P3, the same as P4, the same as P5. That would be 1/4. So this is a uniform distribution that has everyone at 20%. They all have 5 slots. This is a very skewed distribution, and each one of them is 99%. The other ones are extremely small. And this is something in between. Yes?
So you take the 20%, subtract each one of them and take the modulus and add them. Like 29 and 1. And then add them. And so
So you mean average, some sort of average standard deviation. How close are those things to the mean being 20%? That's a heuristic, you just made that up?
Yeah.
Very good. We can make up things, that's good. I want to know if anybody knows how to do this. Heuristics are good, but you should know what people have, like mathematicians have actually done.
Use entropy.
Very good. They choose entropy. So for each one of these distributions, I can compute entropy. Entropy of distribution is what? What's the formula? I go over all the slots, right? And it's who? Pi, 1/Pi. And this, of course, I can measure it here. When is the entropy going to be high and when is going to be low? Which one of those will have high entropy and which one of them will have low entropy? Somebody else. Yes.
Where the probability is 0.5 to have a high end.
0.5? Meaning uniform.
Uniform, yeah.
That's be high entropy. H is high. And this one will be H low, right? Because it's the most skewed one. And presumably this is somewhere in between. You should verify this. Take that formula, apply it to those 2 distributions and see if that works out. So back to my problem here. I would like to measure the entropy of my data labels. This distribution here, it's only concerning the labels, right? 60/40 has to do with spam versus not spam, or sick versus not sick. This is not the distribution of some feature or the patient's involved, just the distribution of labels. Label distribution. So I would like to say that my entropy here versus here, what happened to the entropy? My purpose is to decrease the entropy. Except this is the data has in here 1 bucket, 60/40, and in here has 3 buckets. So how do I measure the entropy on these 3 buckets? I mean, the data is the same. If I put all my data together, I get 60/40. Because all the data points from here are in one of these buckets, right? So how do I say, okay, I decrease my entropy, but I have to be able to measure entropy over 3 buckets somehow?
Information gain.
By the what?
Information gain.
I don't know what that is. Yes.
You do a weighted average of the entropy by the number of data points.
Very good. Is that something you made up or you know about it?
I think I've seen it used for some
Right.
reason.
I think he's right. I think that's what people use. They say, do the entropy here, do the entropy here, do the entropy here. Can I just average or add up these entropies? Why not? These might have 80% of the data in it, right? So I have to create a weighted average of this entropy. I can say I can measure the entropy here and here and here, but I have to weight with how many data points are actually in that bucket, which I know. Right? So I could come up with some sort of differential, criteria here for split. Measure the entropy before the split. Right? That one, 60/40. Minus the average, how do I say that, the average? It's the weighted sum over the branches, the entropy in each branch, times the proportion of data in that branch, right? Saying measure the entropy of this branch and weight it with how many data points are in here, divide by the total number of data points. So now its difference is the one before minus the weighted average of the entropys for each branch. That's what somebody said, is that information gain? Yes. I think that's the one, right? I think the names are irrelevant here. It's very easy to get stuck into what's information gain, it doesn't matter. You should understand the principle. You can call it a pineapple. If you don't like the name information gain, call it something else. But you should know what is the purpose of it. The purpose of it is, on average, to be more skewed on labels than we were before. And by the way, there are many other heuristics one can design that achieve the same purpose. It doesn't have to be exactly information gain. But this has an interesting property. Any split will achieve a positive difference. Because a split clearly favors labels. Like in the worst case, if I do a dumb split, I get 60/40. But any reasonable split will achieve a difference. So you can expect information gains to be positive. All right? So that's pretty much on this board how decision trees work. We start with a lot of data. We want to split it and split it and split it. We have to be smart about when we stop, because going way too down, we don't achieve anything. Question?
Can it return to the same level? Like if you're like two levels of splits, it can go like it started at one point and then come back to the same.
To mean I went down too much split and then I give up those splits. I say don't use them.
Or you go down two levels. You say you start at 60/40, then it goes to like 70/30, then it comes back. To
No.
60/40. No.
Once, because the information gains are positive, the more I go down, the more this is going to be skewed. So that's easy. Goes in the right direction, even if we choose bad splits. But the splits increase the complexity of the tree, which makes it. We want to do this fast. It's easy to get down with a lot of splits. It's hard to get down with very few splits. Also, another observation here, it might be that I may use the same feature twice. Right? It's possible that I use feature number 2 here with some threshold, and later on the same branch, I use feature number 2 again with a different threshold. Right? It might be the age. This is all the people who have at least 20 years old age. And later on, I say, okay, these are all the 20-year or older people, but I want to distinguish between the ones that are older than 40 or younger than 40, even though everybody here is at least 20. So it is possible to see the same feature on the same path. Question?
So do you brute force the order of the features too?
We don't need a particular order, because if we try all the features with all the thresholds, and we keep track of which one worked best, it doesn't matter in what order we try them. However, once we pick a feature, so that we do brute force, we try all of them. Once we pick a feature, there might be intelligent ways to go to the thresholds. Even though I want to try all the thresholds, there's a computational intelligent problem there that says, okay, given this feature is numeric, it's people's salaries, right? How do I quickly try all the thresholds that I want to try? That's purely algorithm engineering. It says, I have this data matrix here. These are people's salaries. I decided I want to try that feature for my split, right? I could threshold it, assuming I sorted by this column, I could pick different threshold to sort it, right, and split it. Of course, wherever I pick the threshold, this data will go left, the other data will go right. Once I have a feature threshold, I can measure my information gain or my criteria. I would like to try a different threshold. Is there a way to use the previous threshold? That's my question. You have this question or some other question?
No, I was thinking about binary search.
Right. So I would like you guys to think when you implement decision tree, which you have to do for homework 1, I can tell you in advance, don't try to be intelligent about features, because you have to try all of them. So one by one, no hope in that. But once you pick a feature, say I want to try different thresholds. Can I do binary search? Would that be faster? Can I move, when I move the threshold from here to here, can I say, well, wait a minute, all those points are going left, are still going left. All those points are going right, they're still going right. These ones were before going right, and now are going left. Can I update my calculation somehow only for the points between the thresholds to not do the whole thing again? By the way, these kind of things won't be a big deal for the homeworks. When you show your homework to the TA, we won't grade the efficiency of your code. Because if we do, that's going to be bad. No. There's nothing to do with your ability. This is the first machine learning course that assumes that you've never done machine learning before. And I can tell you from my experience and my PhD students' experience, and Ketchin can attest to that, to get to the efficiency issues, you gotta spend a few years doing machine learning. It's unreasonable to ask you guys in the first course to do an efficient decision tree algorithm. Microsoft came up with something, I think it's called Boost something tree, a very efficient algorithm. That was after 30 years of decision trees. Okay? So these people are still working on engineering of how to do this fast. And currently the faster way is don't try all the thresholds. Pick the min and max values on that feature column. Split that interval into 100 possible thresholds. And then try this 100 and don't really try every single possible threshold. So this is still a hard problem how to do it efficiently. That's why if your code works and your decision tree works and gets the expected result, we won't grade. Maybe we give you extra points if you do something fancy, but we won't penalize if you're very slow. What's gonna be an issue is your hardware. If you have a laptop with only 8 gig of RAM or something like this, and you do something that you're not supposed to be doing, you're not gonna be able to do it the time. But other than that, it won't be part of the grade. Okay, so this is brute force. You can try to be intelligent about how to try different thresholds, but it's no point in trying to be intelligent about features. Let me see, we have to stop when? 4:25 or 4:30? 4:30, all right. I want to say one more thing and then connect my projector. That I can say again next week. What if my label, so this clearly makes sense for patients that are sick or not sick, right? Also for spam emails that are spam or no spam, or for images that have tigers, don't have tigers. Can I do this for the multi-class problem, RGB, KY? Can I repeat this whole thing if my classes are 3 classes, RGB? This will be a distribution over 3 labels. This will be 3 labels, 3 labels. I think this whole thing will work out with entropies and information gain, even if I have 3 categories instead of 2. Hands up who's with me. Hands up so I can see them. Don't be shy. If I have 3 categories instead of 2, can I do the whole thing with entropies? I can. How about if I'm trying to predict a quantity, like a salary? Here's a person, he has this degree, did this, has the experience, blah, 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 here's his age, all the features I have about the person, and this is 122,000 salary for that person, or the house price, right? That's actually a data set you're gonna have. These are houses, number of bedrooms, color, square footage, whatever people care about houses, and the label is the house price. Does it make sense to do this? Can I do this for house prices? How do I do this if my label is a quantity, like 120,000?
It's the same deviation, population bucket instead of the entropy.
So I still want to do splits. The idea of the data structure of the tree is the same. This is all my houses. Some houses go this branch, some houses go this branch, some houses go this branch, right? And then I stop when I have some consistency, or the consistency cannot be measured with entropy anymore. I think that's your point, right? The split will work the same, right? In here, the split might be the patient blood pressure, and the houses might be the number of bedrooms. If it's less than 3 or more than 3, that would work. But this criteria here doesn't work, right? I need a different criteria. So how do I say consistency when my labels are quantities? What's consistent? If I say you're gonna have 1,300 houses, and all houses have different prices. We need a different mathematical measurement for consistency. In here, consistency is entropy, right? If entropy is low, it means everyone was effectively of that category, right? If entropy is very low, means everyone was red, or blue, or green, but one color. So entropy will measure how consistent things are. Consistent is the opposite of uniform random. Uniform random has high entropy. Consistent is almost not random. Everybody in that bucket is, red. For what you were saying, for house prices, we can't use entropy. What do you mean? What do you mean by consistency? If I have 1,000 houses, how do I say all the prices are roughly the same? Variance, right? I look at those prices, I measure the variance, and what's consistent, the low variance or high variance? Low variance means what? All the prices are close to the mean. So this is another thing that I expect you to know, or if you don't know, to go home and quickly figure it out.
Does the order that you pick, what like feature you're gonna split on matter? Because like for houses, square footage is like a really good indicator, right?
It matters, but we're not going to impose human knowledge. If you're a realtor, you're going to know square footage is the first thing I try to do. In here, we still do brute force, and we let the algorithm figure out which feature is the most useful right away. We implement this greedily, which is a problem. You may argue that even though that's the best split you can do right now, overall, for the tree would have been better to try a different split first. But in a greedy fashion, we try all features, including square footage, and if really the square footage makes the biggest decrease in consistency, biggest increase in consistency, that's the one we use. If it's some other feature, we use that one. So we tend not to use domain knowledge, like doctor knowledge or realtor knowledge. We just let it run. So how do I do the variance thing again? What would I have to measure? How do I adapt this formula for a quantity? I measure variance in here, and then some sort of variance here, and here, and weight it out, right? And then if that variance decreases a lot, I call it the big progress. So depending on how much the variance decreases, that's what characterizes how good my split is there. So I have this in a slide. Let me connect this.
Also, mention how you pick the salary once you got things.
Right, so suppose you're talking about this salary, the quantity, right?
Yeah.
So suppose I organize my tree and I have these buckets. In here, everybody has salaries, presumably more consistent, right? Like everybody in the bucket should be roughly the same salary. I take my next person, I put it to the tree, I end up in this bucket. What should I predict? The mean of that bucket, right? The average on that bucket.
Can you also say that it's gonna lie between like
Sure, I can get the confidence.
Okay.
Right, depending on how the values in that bucket look like and how many data points are there, I can compute the confidence. Decision trees are not particularly good for confidence, but if the bucket is big enough, sure. That's our website. I showed you this last time. There's a bunch of stuff that you can click on. You can get slides here. There's the slides I've been using with examples how decision trees work. Those are not better slides than other slides. I wouldn't say. I think in the terms of decision trees, there's many good tutorials even on Wikipedia. You don't need a textbook for this. I'll tell you when you need to read something in particular. For decision trees, there are many basic description, high school level, that will do the job. What I want to point out is it says here, here's a particular example which is categorical and has some numerical features. These are cars, this is the LPG, the cylinder, this one, and so forth. And you can see how this plays out in a tree. Depending on what I try to split, this is going to be the counts on good versus bad for those cars instead of proportions. So you can go through these slides. What I want to show you is this part with the values labels being quantities, right? So if this is how I estimate the prediction for a particular bucket, right? If a data point went in there, I'm gonna do the average in that point, right? And this is how I calculate the square mean loss. That is the same as variance, right? Or very close to variance. That's saying here's the salary or the quantity I've got minus the mean square, and it's divided by how many things I've got in that bucket, right? So how do I do a tree for quantities? I'm going to measure this loss, and every time I do a split, I'm going to get this average for each bucket weighted. And I say, if ideally, consistency will mean that all the items in the bucket are close to their mean, right? So even though before the split, some items, imagine a very simple problem where some people have high salaries, $200,000, and some people have small salaries. If I compute this quantity before the split, I get a large variance. But if I manage to get a split that quickly groups the people with high salaries together and small salaries together, that will have a very small error measurement here, right? Because if all the people have high salaries in a bucket, they're going to be all close to their mean. That's very close to zero. And in the other bucket, the small salaries will be very close to the mean, to their mean. That's also going to have small variance. So it's possible if I get a feature that's very correlated to the labels to get in one shot from a large variance to a very small variance. That would be an easy problem where with one split, I kind of manage to do my classification. And we call this a regression tree. So here's a basic example of how this stuff works, right? These labels here are quantities. So if I have this kind of, in here I have some small values and large values. If with one split, I manage to put those low values in one side and the big values on the other side, then I can get very small errors compared to the error I have before the split. So that's one thing. The other thing I want to talk about is homework 1. Some of you, I'm sure, have seen it. There's two data sets here. The spam-based data set you can download from this website here. I think it has about 44 or 5,000 emails and about 50 features, and they're all labeled spam or no spam. The other data set, the housing data, it looks like this. And you have to, there are not that many features here, but they're all numerical. We're going to use these data sets for few problems. Problems 1, 2, 3, and 4 are 1, 2, and 3, I think. 1 and 2 are the programming exercises. So let's see what those problems are asking you to do. This is the one that says build a regression or decision tree. So for the housing data set, it would be a regression tree. For the other data set, which is a spam, that will be a decision tree. And for this, we're going to implement linear regression. That's going to happen next week when we're going to talk about it in class. On these algorithms, you have to implement them from scratch. So you can use your favorite language and data structure that's available, but that data structure can be a tree, a machine learning tree, because that's too easy. So the difficulty is that you're going to have to put it from the foundation together. And I think most students in previous years found it easy to run on the side regression or decision tree package. Python has a machine learning library, scikit-learn, that's very easy to use, right? So you can use that one to get a sense of what you should expect. The TAs will also point out what kind of performance they want to see, but it's clearly going to ask you to see your own code. Where is the split? How do you manage entropy, information gain, so on and so forth. In regression, we're going to see next week, there's the square mean loss, and you have to take derivatives or use normal equations. You're going to get. So the first two problems are programming. I decided that some problems are where it says graduate only. The undergraduate students in the class do not have to do this problem. So you can get your grade computation won't include this problem. But there's nothing for the undergraduates here stopping you to take a look at it and even do them or submit them to grade to get the grade on them. The problems marked GR only, they won't be included in the grade computation for undergraduate students. And there's extra credit problems that not worth any points. So there's a not for the credit. It's only for the people who found the class too easy and they want to do some other interesting stuff. But you won't get points by doing so. So the grade is only computed for the non-extra credit problems. So those could be, some of those are mathematical. Even here for the regular credit, if the problem is not programming in nature, you have to submit this somehow on paper. You can write it with a program like LaTeX or Word, or you can write it by hand and scan that, call it problem 4, and put it in the Dropbox folder there where you have it. So this clearly is not a programming problem. It's asking you for a mathematical argument to do something with the tree. Where it says things like DHS, that refers to a textbook. That it's not mandatory. So we have here 2 recommended books. That's the DHS book. This is the Kevin Murphy book. You don't have to buy those books. And if you want those problems and you can really get access to them, which I doubt, I'm pretty sure if you want to find problem 8 from chapter 7 of this book, you can find it without buying the book. But I can give you that problem. You don't have to buy the book for that reason. I think those books are very good. They definitely worth studying, but they're too advanced and too big for this class. So if you buy this book, we're only going to talk about a few parts of it. They're worth going to them, but you don't need them to get an A in this class. If you just do the notes and the homeworks, that's enough to get an also have here the sessions. I think we're doing today. That's what's scheduled. Rider 268, and only Wednesday we have a different room. We're gonna ask students to come. If you wanna come to the office hours that day, either come reasonably early, say before 7 p.m., or at least let know the TAs, hey, I wanna come, but I can't come until 8 p.m. Because if nobody's there by 8 p.m., they're probably gonna leave. They won't stay more than that. Okay? But if you are there, they will stay until they make you happy. Oh, there's a Piazza post, Piazza link. I think everybody's got to it. That's where the discussion is gonna happen. And that's where, expected results are gonna be posted. Not right now. I typically do projects for people who are ready. Once you sort the data, right, what you're going to do, you jump over a bunch of
Yeah.
So conceptual see
the features are not
try every feature, consume the features.
but you don't know more. You don't know the feature.
That's true. You can just approximate, you find the local maximum.
I'm not sure how you move this.
Well, that's stochastic gradient descent.
I think that needs to some. Right. Without assumption.
Stochastic gradient descent is used to find the local, to find a maximum minimum. Finding the entropy of information gained for a specific threshold and also do not functions. Like, there would be ways to approximate.
Okay.
I'm not trying to say
Try it out. Yeah, see how it works. But I think for most problems, you rather have to try enough thresholds. People may skip some of them.
Right. Like you said, going through 100 different ones between the maximum.
Right. But then the problem is one of these small buckets may contain a lot of data and some others no data. So I think you have to try enough thresholds for the homework one to get the performance that the TAs expect. How you do it is something.
Right. Okay, awesome. Thank you.
You guys can talk to me, but I need to shut down the camera. So, anyway.
These two winners.
Yeah, but I need to shut down the camera.
So you talked about local and global minimum or maximum, like the optimal solution for like how you should order the tree.